In this video, I'll introduce the concept of complex differentiation, which looks very familiar. It looks like real differentiation. And a lot of the rules are the same, except complex differentiation is a little bit more restrictive. So by the end of the video, you'll see that it's actually a different concept. Okay, let's jump right to it. Okay. So starting with just a review of what real differentiation is like. So suppose we have a function f, and let's pick a point x naught in some open interval. We say f is differentiable if this limit quotient, the limit of difference quotient exists. And roughly what this means graphically, we can graph it because it's a real function, is that if you zoom into a point x naught, the graph of the function is very similar to a straight line function. That's what that means. Okay, so hopefully that's a review. So very natural definition for complex differentiation is to just look at that limit and make x into a z, make it a complex number. So that's how we're going to define complex differentiation. So we say complex valued function f is differentiable at z naught if this difference quotient limit exists. But here, we're taking the limit as z approaches z naught in a complex sense. So it's a little different. Right. If it exists, we're gonna denote the derivative with f prime, df dz, or ddz of the function f evaluated at z naught. So all of these are familiar notations we use for real differentiation. Okay, also, it is equivalent to taking this limit. So you might be more familiar with dividing by h and adding h to z naught. This is totally equivalent. You just replace h with z minus z naught. And then the limit as z approaches z naught is equivalent to limit as h goes to 0. So this is the equivalent limit. The only thing is that, again, it's only equivalent if you consider h to be a complex number. So it could approach from the imaginary axis as well as the real axis, or any other direction in between. Okay, so let's look at some simple functions. If we have a constant function f, then the derivative is going to be, well, it's constant minus constant on the numerator. So we're gonna get 0 no matter what we divide by. If we have the function z, we're gonna have z minus z naught divided by z minus z naught. That's going to be 1 any day. So that's the derivative of the function z is 1. Derivative of the function z squared. We have z squared minus z naught in the numerator. So this is starting to get a little bit more complicated, but if you factor z squared minus z naught into these two factors, one of them will cancel out. And as z approaches z naught, we're gonna get 2 times z naught. Okay, so far, derivative of constant function x squared are 0, 1, and 2x respectively. Like so far, it's following the exact same pattern. In fact, you could get the power rule here. So you could prove it exactly the same way. You just have to know that zn minus z naught to the n factors into z minus z naught, which could be canceled from the denominator. times z to the n minus 1 plus z to the n minus 2 z naught plus dot 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 zn to the n minus 1. So if you happen to know this factoring technique, the z minus z naught cancels out nicely, and then you'll get n different terms left over with a z naught to the n minus first power. So you'll get the power rule back as it is with the real differentiation. And thankfully, other familiar rules follow. So if you take the derivative of constant times a function, you just take the derivative of the function and the constant is unaffected. It stays in front of the function. You could take the derivative one function at a time if the two functions are added together or subtracted. If you have a product rule works just the same. And quotient rule also follows in the same way. And also the granddaddy of derivative rules, the chain rule, thankfully, is exactly the same. And I'm not going to prove them. It's exactly the same proof as it is with the real differentiation, because all the limit rules are the same. So the proof is just replacing x with a z. Okay, so that means we could take derivative of polynomials just fine. Yeah, so we just have to use the power rule. Okay, and if we could take the derivative of 1 over z as well, because that's a constant divided by polynomial, right? Like z. We know how to take the derivative of z, and we know how to use quotient rule. So it's exactly the same. The chain rule works, so we could do that. Squared minus 1 to the second power times the derivative of the inside. If you're rusty with all of these rules, as you might be, then maybe practice might do you good. But I don't think there's any surprise here. So I could use the quotient rule here. So low d high minus high d low over square of what's below. Okay. So all of these rules carry over. Now, just to prove to you that complex differentiation is really different, we really have to look at new type of functions. So let's look at it. Let's look at the real part function. So this is a function that takes a complex number and just give you back the real part and just kind of throw away the imaginary part of this. Okay. Let's compute it. So we take the limit, and I'm going to take the limit in the real sense here, because I want to make a point. So limit as h goes to 0, I'm thinking of h as a real number that's going to 0. So the real part of z plus h minus real part of z divided by h. The real part of z plus h is the same thing as real part of z plus real part of h, but real part of h is just h because I'm taking this real limit. H is a real number, and the real part of z kind of cancels out, right? So all we have is h divided by h, which is equal to 1. Okay, so that would be the limit if you confine yourself to the real axis. But because this is a complex differentiation, we have to also consider approaching from the imaginary axis. So let's do that. So along the imaginary axis, again, here I'm thinking of h as real, but I'm adding and dividing by IH. So this is now pure imaginary direction. So we're at, approaching z from vertically, I guess, on the complex plane. Here, what's different is that the real part of this IH is just 0, because if it's a pure imaginary thing, the real part of that is has no real component. So when we do real z minus real z, we just have 0 in the numerator. Denominator, we have IH, but 0 divided by IH is still 0. Okay. And here, there's a problem. The limit doesn't match if we approach from the real axis and the imaginary axis, right? And if the limits do not agree from different directions, the limit itself does not exist. So that means that this function, the real part function, does not exist. Sorry, the derivative of the real part function does not exist. Okay. So now this is different, right? It's so the real part of z behaves like the function x on the real line, right? And the derivative of x is 1. But the derivative in the complex sense of the real part of z does not exist. So that's something that's different here. Also, I'd like to point out that if you look at partial derivatives, the partial derivative of this guy exists. The partial derivative is 1 and 0 respectively. But complex differentiation is different from that as well. Okay, so let's look at the complex conjugate function. So this doesn't do anything to the real part, but you switch the sign in the imaginary part. Okay, again, I'm gonna break down the limit into approaching from real axis and imaginary axis. So if thinking of h as a real number, if you take the limit, the complex conjugate of z plus h is same thing as complex conjugate of z plus complex conjugate of h. So the complex conjugate of z cancels out. Since h is a real number, complex conjugate is still just h. Denominator is h, so it divides to be 1. If we approach from the imaginary axis, now when you take the complex conjugate of this part, we get negative IH. And if we divide by IH, the limit is negative 1. So the complex conjugate function does not exist either. So the limits do not agree. The complex derivative does not exist. Okay. A theorem here. If f is differentiable at z0, then it is continuous at z0. So this is a useful fact, which is also true in the real derivative sense, but let's prove it. So differentiable means a particular limit exists. So we have to use that in the proof. Okay. So basically, to show that something is continuous, we want to show that this limit as z approaches z0 is equal to f of z0. The limit agrees with the actual value there. That's equivalent to saying the limit of this difference is going to 0. It's just a different way to say the exact same thing. We're writing it this way so that we could use a trick here. What we could do is we can multiply and divide by z minus z0. Okay, so I'm multiplying top and bottom by z minus z naught. I'm doing that so I get an expression here that looks like a difference quotient. And if you take the limit, we know the limit exists because it's differentiable. That's given in the part of the hypothesis. So this part has a limit. It approaches f prime of z naught. And this part also has a limit. I mean, if z is approaching z naught, it's approaching z naught minus z naught. So this part is approaching 0. And if you take a limit of two things that's multiplied together, each has its own limit. The limit is the product of the limits. And it doesn't really matter what the derivative is at this point. You're going to multiply by 0, so we're going to get 0. So what did we show? We show that this limit is equal to 0. Hence, the function is continuous. Okay. I'm going to make a important definition here. So if you have a complex function, u to a complex number, and here I'm taking u to be an open set. We say it's complex analytic or holomorphic. They both mean exactly the same thing. So it means within that open set U, it is complex differentiable everywhere in that set. So it's important that we're not just talking about a point here. It's not complex differentiable at one point. We say it's analytic if it's differentiable in like a cloud of open points. So it has to be differentiable in a small patch, at least. I hope that makes sense. And furthermore, if the function is complex analytic in the whole complex plane, then we call it an entire function. So it's this notion of complex analytic is slightly stronger than just being differentiable at one point. It's differentiable in a small patch of points, at least. Okay, so some examples. Polynomials are entire. We've already shown that the power rule works, so all the polynomials have derivatives. Rational functions. So if you take polynomials and divide by polynomials, it is still analytic because the quotient rule still holds, as long as, of course, that we're not dividing by 0. So as long as you throw those points outside of the domain, we have analytic function there. Okay, and a lot of the function that we introduce in the complex setting, it's not analytic. The complex conjugate function, the real part function, and for the same reason, imaginary function, they are all not analytic. Okay, let's look at the modulus function. And modulus function behaves like absolute value function on the real axis. And we know that absolute value function is not differentiable at 0. So you might also already guess that the modulus function is not differentiable, at least at the origin. But let's look at what it looks like outside of that. And also, actually, if we square it, the absolute value square function is differentiable in real sense. So maybe it is differentiable. Let's investigate. Okay, so okay, and another way to think about this is that you could think of modulus squared function as z times the complex conjugate z. So we know z is differentiable, z bar is not. we can't use product rule because one part of it is not differentiable. So you might guess that, oh, maybe it's not differentiable. Let's see what happens. Okay, so we have to use the difference quotient. And instead of looking at z plus h modulus squared, I'm going to rewrite that as z plus h times z plus h bar, and then multiply it out. So we have, these are the cross terms, and we'll have 4 terms if we FOIL it out. Z times z bar is same thing as modulus z squared, so those two cancel out. What is left? Well, let's see. These two terms have h in it, so we can cancel out with the h on the bottom. That's those two terms. We have one more term, z times h bar over h. Okay, so let's try to analyze the limit as h goes to 0. This thing is suspect, right? Like when we had complex conjugate, if we're approaching from the imaginary axis and the real axis, those are going to have different limits. So when z is not equal to 0, I'm multiplying by z here. So you could make this part approach 1. You could make that part approach -1, depending on real and imaginary axis. This thing does not have a limit if we stay away from 0. Okay, but if z is equal to 0, then the problem part just kind of disappears from the difference quotient. And well, if z is 0, the z bar is also 0, and h bar approaches 0. So the derivative would be 0 at 0. Okay, so it is complex differentiable at 0. We still would not call this function analytic. It's not analytic because it's only complex differentiable at one point, at the origin. And it's not an open set. Remember, for it to be analytic or holomorphic, it has to be differentiable in a small patch of points or some open set. And this guy is not. So the modulus square function is also not analytic, although it is complex differentiable right at the origin. Okay. All right, so that's complex differentiation. There's a little bit more to explore here. We know that all the real functions, well, at least the polynomials and rational functions, has derivative as it did before. Some of the complex functions that we've introduced does not have derivative. We have to look at other functions and see if they are still differentiable in complex sense. We'll start that next time.